All right, we're going to look at a combustion reaction, right? That is when a fuel burns, okay? And the fuel we're going to look at is propane. Propane is made from carbon and hydrogen. It's a hydrocarbon. And it happens to be C3H8. That is the formula for propane. And when you burn something, okay, a combustion reaction, it means it's reacting with oxygen, okay? So we can write our formula as the fuel plus O2. That is a combustion reaction. And what happens in any combustion reaction, you've got the fuel, which is some organic compound, organic meaning it's got carbon, hydrogen, and often oxygen as well. And when that burns with oxygen, it always produces carbon dioxide. You know, you can think that oxygen joins up with the carbon, with the hydrogen, and you have carbon dioxide and water. Okay. Now, of course, the water, you know, since this is with a flame and everything, this is hot, and the water is as vapor. Okay, so we don't see it like dripping and getting wet when you burn something, because it's a vapor, and that goes off with the smoke. But the carbon dioxide also goes off, and we want to know how much carbon dioxide are we actually releasing into the air when we burn propane, for example. This is the substance that is in many propane cylinders, like you might take for your portable camping stove or something along those lines. All right. But first, okay, we know that it reacts with oxygen and it produces carbon dioxide and water. Okay, but what proportion, you know, how much carbon dioxide, how many molecules of carbon dioxide are produced for every molecule of propane that is burned or combusted with oxygen? Okay, so we have to balance this equation. What that means is it comes from the law of conservation of mass or matter, saying that here, you know, I have 3 carbon atoms on the left. I'm only showing 1 carbon atom here. So the way I've written this equation, I'm actually destroying 2 of those carbon atoms, and I can't do that. That disobeys the law of conservation of mass. Okay, so I have to make sure that I have all 3 of those. But I know it forms carbon dioxide, right? That's the substance. I can't change its formula. So I'm going to put a 3 in front, saying that I need 3 carbon dioxide molecules to account for those 3 carbon atoms that I started with. Okay, they're being rearranged. No longer are they all together in 1 molecule, but they're in 3 separate carbon dioxide molecules. Okay, and likewise, I have 8 hydrogen atoms over here. I also need 8 hydrogen atoms here, so I'm not destroying any of those, and those will be rearranged. Instead of all of them being in 1 molecule, they will be in 4 separate water molecules. 4 because each water molecule has 2 hydrogen, so that gives me a total of 8 hydrogen atoms among those 4 water molecules. Right? So then I can go back and make sure I have the same amount of oxygen on both sides. And here I have 4 oxygen atoms, and here I have 6 oxygen atoms. Each carbon dioxide has 2. I have 3 carbon dioxide molecules, so that gives me 2, 4, 6 oxygen atoms there. Plus the 4 is 10. 10 atoms. Each molecule of oxygen has 2 atoms in it, so I need 5 molecules of oxygen. And now what I have is a balanced equation, meaning I have the same number of atoms on the left as I have on the right. In other words, as this reaction proceeds, all I'm doing is rearranging those atoms. Instead of being all grouped up in 1 molecule, now they are dispersed among the molecules of carbon dioxide and water. Okay, but they're all accounted for. All right, now I have a balanced equation. Let's use this balanced equation, and by the way, anytime we want to do a calculation that involves a chemical reaction, we have to have a balanced equation. Okay, if we don't have a balanced equation, then we're not going to be, our calculation isn't going to be accurate because we're not obeying the law of conservation of mass. Right? So we have to have that equation balanced. So let's say we take a, say a 250 gram cylinder. That would be kind of a larger size cylinder of propane. And let's say we burn the whole cylinder, how much carbon dioxide are we actually going to produce from that 250 grams of propane? All right. So the first thing that we need to do is recognize that what these numbers are saying is that for every molecule of propane, I'm producing 3 molecules of carbon dioxide, as well as 4 molecules of water. And it requires 5 molecules of oxygen to combine with that 1 molecule of propane. Okay, so this tells us how many molecules of each type are either being reacted if it's part of the reactants, or will be produced if it's part of the products. Okay, so 5 molecules of oxygen react with 1 molecule of propane to produce 3 molecules of carbon dioxide and 4 molecules of water. Now, that's nice, but on a larger scale, okay, than individual molecules, I can say I have a mole of propane. Okay, if I have 1 mole of propane, a mole is just a large number of molecules, right? It's like saying I have a dozen molecules, right? Well, if I have a dozen molecules, then I'm going to have 5 dozen molecules of oxygen that will react with it. Okay, so if I have a mole of propane, I will have 5 moles of oxygen that must react with that propane, and it will produce 3 moles of carbon dioxide, 4 moles of water. All right, and that's the important thing to realize here, is that these numbers, and this is of course an implied 1, these numbers represent molecules, or moles typically is the unit that we use with them. 5 moles of oxygen react with 1 mole of the propane to form 3 moles of carbon dioxide and 4 moles of water. Okay, I'm starting with 250 grams. So in order for me to use this equation, see, this isn't talking about grams of propane and grams of oxygen. So I need to convert this grams into moles. Okay, now how do I do that? Well, I need to find the molar mass of the substance that I'm interested in. In this case, it's of the propane. All right. So that involves looking up the atomic masses, or the molar mass of these elements. And so for carbon, I'll just write it down here, 12.01 grams per mole. So if I have a mole of carbon, and this number comes from the periodic table, any periodic table will have the atomic mass of the elements. Okay, and if you look up carbon, it'll be 12.01, and the units are grams per mole. That means 12 grams of carbon represents 1 mole. That means you have that many atoms of carbon in 12 grams. All right. So anyway, we do this also for hydrogen. 1.008 8 is the number that we would find from the periodic table. Again, grams per mole. And we have 3 carbon atoms and 8 hydrogen atoms in a molecule of propane. So we'll multiply those, and what we'll end up with here is 36.03 grams per mole, and then 8 times 1.008 would be 8.064. Okay, we can add these together then to get the total molar mass for this compound, and what we'll have is 44.094. Okay, since I really only have 2 significant figures here, as long as I have more significant figures than what I have there, I won't be introducing rounding errors. So I'll go ahead and we can round off that 4 there, since it's not really significant by this calculation anyway. All right, and so what we'll have is our 250 grams, okay, and what this is, the units again, grams per mole. 44 grams of propane is 1 mole, or 1 mole of propane weighs 44 grams. So I need those grams to be on the bottom so that they will cancel with the grams that I'm starting with. Okay, so grams per mole, I can put this then on the bottom, 44.09 grams to 1 mole, arranged so that it will cancel. All right, so now at this point in my calculation, I have converted to moles of propane. I found out how many moles of propane are in that 250 grams. Now, what do I need? Because now I have moles of propane. I should be explicit here and say moles of propane. But I want to know how much carbon dioxide is formed. Okay, well, that's what the equation helps me out with, because it tells me that for every mole of propane, I produce 3 moles of carbon dioxide. Okay, so I can find a mole ratio there, and that's what I'm going to use here, because this is it's a conversion factor. Okay, it's saying for every 1 mole of propane that is reacted, it will produce 3 moles from that 3 of carbon dioxide. Okay, so I have a 1 to 3 mole ratio, which comes straight from that balanced equation, right? And I arrange it so that my moles of propane will cancel, and I'll have moles of carbon dioxide. Okay, but I want to know how many grams of carbon dioxide are formed. Okay, so here I have moles of carbon dioxide. I need to convert that to grams, and how do I go about doing that? Well, just the same way that I went from grams to moles, I'm going to do that, except arranging it differently so that the moles will cancel this time. I know I need moles of CO2 on the bottom to cancel, and then I'll be left with the grams of CO2. Okay, we're talking about carbon dioxide this time, so I need the molar mass of carbon dioxide. And for carbon dioxide, I have 12.01 grams per mole for the carbon, and oxygen is 16.00. I have 2 of those, so that would be 32, and this will make it 44.01. Okay, just a coincidence that it's very similar to the molar mass for the propane. Okay, 44.01 grams per mole of carbon dioxide. Okay, so we see this process, very common process, grams of the first substance to moles is our first step, the three-step process. Okay, first we convert it to moles. We could say this is grams. To generalize, I'll say grams of A, and we convert that to moles of A. We use the molar mass of A to do that. Then we switch to a different substance. We went to moles of B. All right, just making it general. And then our third step is going to grams of B. Okay, so we see this progression quite frequently. Three-step process. We use the molar mass of A to do this first step. Then we have a mole-to-mole ratio from A to B. That comes from a balanced equation, the mole ratio. And then the molar mass of B will convert from moles to grams of that substance. Okay, so two molar masses and the mole ratio. That is our. Those are the three conversion factors that we use to go for this kind of a problem. Grams to moles of the other substance to grams of that substance. Okay, now let's go ahead and calculate this and find out how many grams of carbon dioxide will actually be produced. Okay, so here we have 250 grams to start with, and then you can read this 250 times 1. Well, we don't have to do that because we know it's the same, and then divided by 44.09. Okay, so we're what we find is we divide by anything that's on the bottom, divided by 44.09, and then times 3, so times 3, and divided by 1 times 44.01. All right, so times 44.01, and what do we get from the end of this? 748.6. All right, 748.6. What are the units? Well, everything has canceled out except grams. So this is grams of the carbon dioxide that we had. Okay, so if we kept this to our two significant figures, we would round this to 750 grams of carbon dioxide. All right, so from a 250 gram container of propane, we release 3 times as much, essentially, of carbon dioxide into the air.